Here we go, Dalton's law of partial pressures, and we're talking about Dalton, who was a scientist that came up with the fact that if you want to figure out the total pressure of a gas in an enclosed container or room, you can simply add up their pressures, and that equals the total pressure. So each gas is going to exert a certain amount of pressure based on its temperature, which is its basic speed, and its mass on the walls of the container. And we can actually measure these. So again, knowing here that the total pressure of a mixture of gases is equal to the sum of the partial pressures of those gases, and this is the equation that you need to know right here, Dalton's law of partial pressures, and we're going to put it to use here in an example problem. So taking a look here, you're asked to find the pressure of oxygen, so that's my unknown, that's my question mark, at atmospheric pressure. Typical atmospheric pressure is 1 atm, and we know this from STP. Remember, we said standard temperature and pressure. STP, standard temperature, is 273 Kelvin, and pressure is 1 atmosphere. Nitrogen gas is exerting a pressure of 0.23 atmospheres, and the CO2 gas is 0.455, so it wants to know what the pressure of oxygen is. So if I remember my Dalton's law, pressure total equals P1 plus P2 plus P3, and this keeps going. If I had 15 gases, it would go for infinity. You can add up all their gases. So I actually need to identify the pressure of oxygen. That's a partial pressure. So in this case, I'm just going to label that as pressure of O2 as your unknown in this case. And that's basically PO3, but oxygen's O2. And I have nitrogen and carbon dioxide, so I can add those in there. Nitrogen is a 0.230, keeping correct significant figures, and CO2 is 0.455. Now, it really doesn't matter what order you put these in, but as long as they're here, and these are atmospheres, right? We do not want to leave any numbers without units. And that is going to equal my total pressure, which I was told is 1 atmosphere, being that it's at STP. So now I can simply grab out my calculator. I'm going to do some basic math here. I'm going to take my 0.455 and add that to the 0.23, and we get 0.685, if you can see that there. So now I have 1 atmosphere is equivalent to 0.685 atmospheres plus the pressure of my oxygen gas. I'm simply going to subtract over the 0.685 so that these cancel, minus 0.685. So 1 minus my 0.685 gives me the 0.13. So my pressure O2 oxygen is 0.315. I'm sorry there, I said 13. It's 315 atmospheres as the partial pressure of oxygen. So that's pretty easy to use Dalton's law there, and you just need to know it and have it written down on our equation sheet. You will also find it on the back of your periodic table. Now, another version, I guess you could call, of Dalton's law is taking a look here at the partial pressure collected over water. So the important thing to note here is if a gas is collected over water, it has to be over water. That's the key factor here. It's also going to contain some water vapor, H2O gas. This must be accounted for in the calculation of the partial pressures. So the partial pressure of water depends on the temperature at which the gas was collected and can be looked upon table A8, page 859 in your textbook. I also provided the table here for you. So if you take a quick look at this, this is something that you could take a picture of or screenshot or in your book, but you have to be given this table. So you can see here there's temperature in degrees Celsius and the pressure in millimeters of mercury or kilopascals for water vapor. So it goes from 0 all the way up to our 100 degrees Celsius, which is boiling. So you're always going to have to reference this table. And the equation that you need to know here for our water vapor is the pressure atmosphere, or this is T again for total pressure, is the partial pressure of your gas plus the partial pressure of H2O. And then it kind of dot as well here, because if I had another gas present, we would account for that as well. This is Dalton's law, just modified knowing that we are specifically looking at the value of water. So let's go ahead and look at an example problem here of that. Again, this is your pressure total, is the pressure of the gas and the pressure of water. Always find the pH2O using the table. So our example problem here is we're going to collect oxygen gas at 739.6 millimeters of mercury. That is our atmospheric pressure. So that is our total pressure of the system. And it's at a temperature of 20 degrees Celsius, and it says what's the pressure of oxygen. Again, noting here that this is over water, okay? So in the problem, or I'm going to tell you that it is collected over water in our example here. So let's set up our equation. The total pressure is 739.6 millimeters of mercury. That is equivalent to the pressure of my gas. That's pressure of O2. I do not know this. That's my unknown. Plus the pressure of water at 20 degrees Celsius. Well, I need to go back to my table and pull up here. Find 20 degrees Celsius. It's right here. And 20 degrees Celsius, and I'm in millimeters of mercury in the problem, so I want to stay in millimeters of mercury. It's 17.5. 20 degrees is 17.5. So I come back here to my table. 17.5 millimeters of mercury is the pressure of water. Now I can simply subtract over my 17.5 to get rid of that, minus 17.5. So this is our easy math here, 739.6 minus 17.5. You get 722.1 millimeters of mercury. And if we're going to be correct in our sig figs, we are subtracting with 1 decimal place. I need to leave 1 decimal place in my answer. So that is my correct answer for collecting water vapor over water vapor. You have to account for that. Short and sweet video here. Easy equations to use. Make sure you get them written down.